Welcome to ScaleUp University. Welcome to the course on designing data intensive applications. So this is the lecture 9 of module 1, and in this lecture we will be discussing techniques for building reliable systems. So let us look at the lecture overview, like what this lecture is about. So see, this lecture is about techniques for building reliable systems. So reliable systems are not lucky, they are designed. So reliable system is not something which is lucky, meaning to say that it's not a side effect. Like let us suppose we are building a system and reliability we got it for free as a side effect. It is not like that. It is not a property you get for free, and it is not a result of good intentions. No matter how good intentions you have, and you are building a system, reliability is not something you can get it for free or you can get it as a side effect. Rather, reliability is something which you can achieve by putting some efforts. So it is a deliberate engineering outcome built through patterns, discipline, and culture. So this is very important. So reliability, see, if we talk about data intensive applications or data intensive systems, they have to be reliable. So in order to make them reliable, we have to put deliberate engineering efforts. It's a result of deliberate engineering outcome. We have to put efforts. So reliable systems can be built through patterns, discipline, and culture. And that is what this lecture is about. In this lecture, we will learn the techniques. We will learn the efforts, what kind of efforts we have to put to make our data intensive systems reliable. So this lecture, it covers monitoring and observability, graceful degradation, fail first versus fail safe design, redundancy strategies, isolation techniques, reliability as organizational culture. So all these topics we will discuss, and these are the techniques, because every topic you will discuss, you will see, you will learn so many interesting techniques which we will be using for building reliable systems. So this is the module 1, trade-offs in data systems architecture, lecture 9, techniques for building reliable systems. And we are starting with the first topic of this lecture, monitoring and observability. So see, monitoring and observability both are different, rather very different. If I talk about monitoring, so monitoring means collecting predefined metrics. So like in the system, we predefine some metrics, and monitoring is all about monitoring those metrics in the real time, collecting the values of those metrics. So collecting the predefined metrics, it is monitoring. Alerting when thresholds are crossed. So when we are defining the metrics, we are also defining some thresholds. So monitoring is all about always looking at those predefined metrics, collecting its values, and alerting when thresholds are crossed. For example, CPU usage greater than 80%. So CPU usage is a predefined metric. Monitoring means in real time collecting the CPU usage, and let us suppose the threshold is 80%. So whenever the CPU usage is more than 80%, alert will be sent. Error rate is greater than 2%. Latency is greater than 500 milliseconds. So these are like some examples. So monitoring, it answers the question like, is the system healthy? Because monitoring is all about keep on looking at predefined metrics and alerting when thresholds are hit. So monitoring answers, is the system healthy? So that is what monitoring is. But if I talk about observability, it is different from monitoring. So ability to understand why something is wrong. So observability is the ability to understand why something is wrong. Observability is designed to explore unknown unknowns. So see, observability is much more than monitoring. In observability, we try to decode the root cause of the problem. We try to understand why something is wrong. Monitoring will tell that okay, something is wrong, but it will not give you the reason. It will tell that okay, because it is collecting the predefined metrics, and you can set the threshold. If threshold is crossed, means something is wrong. So monitoring can tell you something is wrong, but observability will tell you the root cause of that, why it is wrong. So it is designed to explore unknown unknowns. So if we talk about observability, it will require monitoring, like it will require metrics, wherein real time watching of metrics we have to do. It will also require logs, traces, and contextual information. So for observability, we should have traces, logs, metrics, contextual information, because with this data in place, we will be able to decode the root cause, the reason for the error. So observability, it answers why is the system behaving this way, or the root cause of the problem. So now I think the difference is very clear. Monitoring is just about checking whether the system is healthy. Observability is about why the system is behaving this way, the root cause, the cause. And now it's very clear that observability is very critical. Like in data intensive applications also, observability will play a very big role. So if we want to build reliable systems, for reliable systems, observability is critical. And okay, so let us understand what do we mean by reliable system. Reliable system is the one which will behave, which will keep on working despite of errors. So reliable systems can tolerate the fault. They have fault tolerance capabilities. And let us suppose if the system breaks also, it fails very gracefully. We call it graceful degradation. So a system on which we can rely upon, that is a reliable system. So observability is very critical when designing reliable systems. And why observability is critical? Because see, the idea is that the failures, they rarely look like disk crashed. Because see, whenever any failure occurred, i- we will not get to know the reason. Rather, we have to decode the reason. Because when any hardware component fails or software bugs, it cascades. Then what will happen is that we will be able to see some patterns like latency spikes. We will be able to see, we'll be able to see some partial errors, and strange inconsistencies we'll be able to see, and we have to decode the reason for that. So failures, they rarely look like disk crash. Rather, whenever any component fails, or any uncertainty happens in the system, we can look into it via metrics like latency spikes, partial errors, strange inconsistencies in the system. And without observability, it is nearly impossible to decode the root cause of such uncertain behavior or of such strange inconsistencies in the system. So without observability, debugging becomes guesswork. We have to just keep on guessing. Recovery will be slow and trust erodes. Because with observability in place, we can identify the exact root cause. So we can recover. Because once we know the root cause, the problem, we can very easily solve it. We can very efficiently debug. So the key design principle we should consider: instrument everything that is important. So for observability, what we should do is that we should instrument everything that is important. We should log critical state transitions. We should monitoring business level metrics, not just infrastructure. And we should alert on symptoms, not noise. So this is very important. Like any symptom also we are getting, we should alert. So not only anomalies, but symptoms also we should alert, so that system it is aware, because these symptoms can lead to massive outage. So one of the technique for building reliable system is observability. So we saw the difference between monitoring and observability. We saw the importance of observability, why observability is critical, and we also saw how we can introduce observability in the system. Graceful degradation. So graceful degradation is also one of the techniques for building reliable systems. So what is graceful degradation? So graceful degradation means instead of full system crash, in graceful degradation, system will reduce functionality, maintaining the core operations. So that is graceful degradation. So graceful degradation is instead of full system crash, system will keep on reducing the functionality, maintaining the core operations. Let us look at with a real world example of a e-commerce site. So in a e-commerce site, let us suppose recommendation engine it fails. In a e-commerce site, we have a recommendation engine which recommends products. So if recommendation engine fails, the system should not stop working. The e-commerce site should not go down. Rather, it should keep on working. Only the recommendation component should not work. So the system should be able to isolate the problem, and checkout should still work, and the website should still work. So that is graceful degradation. Like any component got failed, we reduce the functionality, we reduce the recommendation engine functionality. So rather than the full system crash, we reduce the functionality, maintaining the core operation. The core operation is still in place, wherein users they can explore the product, they can add it to the cart, and they can check out. Similarly, if search index fails, the website should not be down. Basic browsing should still work. So that is graceful degradation. So graceful degradation is very important. Why it matters? See, the idea is that users, if we talk about now, they can tolerate reduced features. Like if recommendation engine is not working, it's fine for user. If search index fails, it's fine for user. System should work because users they can tolerate reduced features, but they cannot tolerate complete downtime. Let us suppose I want to shop. Like I visited an e-commerce website. I want to do the shopping. If the complete website is down, my trust will erode. I will not tolerate that. I can tolerate the reduced features, and hence graceful degradation is very important. So whenever you are building data intensive applications, data intensive systems, you should have graceful degradation. It is one of the technique for building reliable systems. Now, what are the design strategies? Let us discuss for graceful degradation. So in order to implement graceful degradation in your system, you should have fallback responses. Now, what are fallback responses? These are like alternate responses. Like when a primary service fails, the system provides a good enough alternative. So instead of an error message, a user might see a static page or something default, which will still maintain the user experience. Because instead of an error message, if we have some static page, that is the fallback responses. Is very important because it has a psychological effect. User might get frustrated looking at the error message, but a static message or a static page can still, the user can tolerate it. Hashed data if live database is unavailable. So let us suppose the live database for some reason it is not unavailable. It is not available, it is unavailable, then you can make use of the cached data. So that is one of the design strategy for graceful degradation. Read only mode during write failures. So let us suppose because of some reason, like database is down or some reason we are not able to write, then at least read mode should be on, so that at least the users they can look into they can at least explore the products. They can walk through the e-commerce site. So the idea is that any failure we should not like make the website down. Like write failure is there, It's totally fine. Let show must go on. The e-commerce site should be live. The read only mode should be active so that at least they can walk through the website, they can walk through the products, they can add to cart. And then what we can also do is that there the transactions, whatever write, we can write it somewhere else. Then later when the database is available, we can transfer that data to the original database. Circuit breakers to stop retry storms. So this is very important. So we already know that retry storms we can get, like let us suppose we have timeouts, like timeout of 10 second. Like I am sending a request, after, I will wait for 10 seconds. I'm not getting a response. I'll send it once again, the request. Wait for 10 seconds, once again. And like let us suppose for a resource, if thousands of users, if the resource is down, thousands of users will send the request every 10 seconds. So the resource will be flooded with user request, retry request. We call it the retry storm. So there should be a circuit breaker for the retry storm. And that can be number of failed requests to a service. Like we can set a number that okay, only 10 attempts I will do. If in 10 attempts I don't get the response, it means something is wrong with the resource. I'll not keep on sending the retry request. So that's the circuit breakers to retry, to stop retry storms. So the core idea when it comes to graceful degradation, so we should design system layers so that non-critical components cannot collapse critical ones. So the idea is very simple. For graceful degradation, the system design should be in such a way that non-critical components, we should be able to isolate it from the system. If a non-critical component goes down, we should be able to isolate it. That's the idea. Fail fast versus fail safe systems. So first let us understand what do we mean by fail fast. So fail fast means system it stops immediately on detecting error. So that is fail fast. Fail fast means okay, any error, just system should go down. So system stops immediately on detecting error. So fail fast system, it certainly prevents corrupted state, because anything wrong in the system will stop. And fail fast system, it surfaces error clearly. So what are the advantages of fail fast systems? It prevents silent data corruption. And how it prevents silent data corruption is anything wrong with the system will go down. So no scope of data corruption, because the fail fast system, they surface errors clearly. Fail fast systems, they enable easier debugging. And what are the example for fail fast systems? Reject invalid transaction immediately. Any invalid transaction, just reject it, because invalid transaction is like an error. So fail fast means any error, just stop immediately. So reject the invalid transaction. On the other hand, if we talk about fail safe systems, here the system continues operating in safe mode. So despite of error, the system will not go down. It will continue operating in the safe mode. So fail safe, since it is operating in the safe mode, the complete system will not go down. Rather, it will avoid catastrophic failure. Thus, the system will maintain minimal functionality, and system will try to isolate the bug, isolate the component which failed. So now it's very clear that fail-safe system, any fault in the system, any component gets failed, the system will not go down. The system will keep on working, maintaining the minimal functionality. System will switch to the safe mode, wherein it will isolate the bugs, isolate the faults, and it will avoid catastrophic failure. That is the fail-safe system. Example of fail-safe system: switch to read-only mode if write fails. Like if we are not able to write to a database because of some, like the database is down, Fail safe means rather than stopping the system should maintain the minimal functionality, switch to read mode, switch to read only mode. So that's the fail safe. So now it's very clear that we can have two approaches: fail fast system or fail safe system. So both have their pros and cons. So if I talk about trade, so there is a trade-off is there. So fail fast, it protects correctness. So in banking systems where correctness is more important, fail fast system we should consider. And when availability is important, like in e-commerce, availability is more important. So fail safe protects availability. Or let us suppose in Netflix or any OTT platform, availability is more important than correctness. Like some lag is there, some jitter is there, it's totally fine. But availability is more important than correctness. So wherever availability is more important, we should go for fail safe. And wherever correctness is more important, we should go for fail fast. And we should even try to combine both appropriately. So the good architecture, like the data intensive system you will be designing, you try to keep both, and you should make use of them appropriately. So fail fast system and fail safe system, these are also techniques for building reliable systems. Redundancy strategies. Okay, first let us understand why redundancy is essential. So see, we cannot afford single point of failure. So single component failure, it must not cause data loss. It must not cause total outage, because a single component failure can lead to data loss. It can lead to total outage. So we should be very careful. We never want total data loss or total outage. So to avoid that, redundancy is important. Now, what are the different types of redundancy that we can have in our data intensive systems? So we can have something like data replication. So in data replication, what we do is we keep multiple copies of data. So that is data replication. Data replication means, okay, we have the database, the master database, that is the source of truth. Now we maintain multiple copies of the or multiple replicas of the master database. So multiple copies of the data is data replication. It protects against disk failure. Then we have service replication. Service replication is the multiple service instances. Like we keep the replica of services. So multiple service instances. So it protects against node crash. So let us suppose a node gets crashed. We have a backup node with the replica of services which are exactly running on the crashed node. Then we have geographic redundancy, wherein we try to replicate the infrastructure across multiple geographic regions. So it protects against data center outage. So let us suppose because of some power loss, some power issue, a region or a data center of a region it is facing outage. Then because of geographic redundancy, we can shift the traffic to the other data center, which is located somewhere in some other geographical area, some geographical region. Then we have network redundancy. Network redundancy means multiple routing paths, so that if any path is having a problem, we should have alternate routing paths. So we also have redundancy trade-offs. See, definitely redundancy is very important, but redundancy do have trade-off. Like what are the benefits from redundancy? Redundancy, no doubt, it improves availability. Because of redundancy, availability will improve, and fault tolerance. But it has downside also. Redundancy, it increases cost because multiple copies, multiple replicas we have to maintain. It increases coordination complexity. and it also increases consistency challenges. It is difficult to maintain copies because consistency challenge will be there. We want that, okay, whatever the state of the original data source, the same state should be maintained by its replicas. That is not that easy. So the idea is very clear that, okay, redundancy, it solves hardware faults, but it increases software coordination complexity. So redundancy is also one of the technique for building reliable systems. Isolation and sandboxing. Now first let us understand what is isolation. So isolation means, like isolation, what it is? Isolation prevents one component failure from spreading. See, the idea is that in distributed systems, components are interconnected. In distributed systems, since components are interconnected, isolation, it ensures that a bug, memory leak, or spike in a non-critical service does not starve a critical service. So, a failure in component A, for example, should not spread. So, the isolation means components, they should be able to isolate. Like if it fails, it should not lead to the complete collapse of the system. Like if a component A fails, we should be able to isolate it, separate it from the system. That is isolation. So isolation is very clear that, okay, if any component fails, we can separate it from the system. We can isolate it from the system so that system still keeps on working, functioning. Now, what are the isolation techniques? So we can have process isolation. So process isolation means, like we can have separate, we can separate processes per service. So we should run services in separate processes. The reason for that is that, see, if we have one process and if we are running all the service in one process, if that process goes down, all the services will go down. So the good practice is that for a service, you have a different process. So separate process per service. So as we can see here, we have service one for process A, like uh, for service one we have process A, for service two we have process B. Now if process A any problem with process A, only service one will get affected. Service two will not get affected. And this is like a very important strategy, isolation strategy, wherein we are doing process isolation. We are having separate processes for separate services. In this way, any process is facing any issue, other services will keep on running smoothly. That is process isolation. Then we have resource limits. So resource limits is also an isolation technique wherein we can set memory quotas. Like for every service, we can set memory quota that, okay, this service or this process, it can only use 16 GB or 1 GB of memory, for example. Then what will happen is that we are isolating. Now it cannot use more than 1 GB or CPU quota, or we can set rate limits when it is trying to hit some APIs. So resource limits, it prevents noisy neighbor syndrome. Okay, and what is this noisy neighbor syndrome? Let us try to understand it. It's very important. Now let us suppose we have multiple resources, like we have multiple processes, they are sharing a resource, like memory they are sharing. You are having 8 GB of memory and multiple processes are sharing that 8 GB of memory. If one process, something is wrong with one process, and if it is trying to occupy more than 6 GB of memory, what if that happens? That can happen. And that is the noisy neighbor syndrome, wherein one neighbor, that is the process, it faced some problem due to some issue. It is trying to, some memory leakage happened. It is trying to use 6 GB of RAM. Because of that, other processes, they are getting affected. So in order to avoid such scenarios, if I set the memory quota, then what will happen? No matter what, that process will not be able to consume more than 1 GB of RAM. So that's the resource limits. Network segmentation. So network segmentation is also an isolation technique wherein we can segment the network. Like here we can see we segmented the network into two zones, zone A, zone B. Now zone A is trusted zone. So there we will keep our sensitive data like the backend and the database, and zone B is the untrusted that will contain the web. So network segmentation, what it does is it limits the inter-service communication. And the good thing about network segmentation is that because in distributed system, it's always advisable to segment networks, because if one network goes down, other will keep on operating. Then we have head, bulk heads pattern. This is also the isolation technique. So bulk heads pattern means we have to partition the system into independent components. So the idea is that if we partition the system into independent components, if one component fails also, the system will keep on running. Let us suppose this system fails, still other independent compartments, they will work. The show will go on. So we saw what is an isolation, isolation techniques like process isolation, resource limits, network segmentation, bulk heads pattern. Now let us see why isolation is powerful. See, isolation is very powerful because see, the idea is that even if one service crashes, even if service crashes, even if I have a service which overloads, rest of the system will survive because of isolation. Because whatever service crashed or whatever service is facing overload, I can isolate it. And because of that, rest of the system will not get affected. It will keep on running. So isolation, it limits the blast radius. Failing of a component is like a blast. Like service crashed, it's a blast. Service overload, it's a blast. With isolation, I am limiting the blast radius because the consequence of that is not spreading across the system. Culture of reliability, SRE mindset. Okay, now we will discuss some very interesting techniques for building reliable systems. So see, reliability is organizational. So what it means, let us understand. See, the idea is that technology alone does not ensure reliability. Along with the technology, the humans, the operations will also decide the reliability. So organizations, they must adopt reliability culture, because reliability is not just about technology, it's also about the organization, like the people, the employees who will be using the system, who will be building the system, because they can also make errors, operational errors, human errors, which can make systems unreliable. So techniques for building reliability, we discussed many uh, technological techniques. Apart from that, we should also focus on reliability culture. So from here comes the principles of SRE mindset. So the idea is that, see, we should assume the system will fail. So whenever we are designing the system, whenever you are designing data intensive system, data intensive application, you assume your system will fail. And when you assume, you will identify that, okay, where systems can fail, you will design fault tolerance. You will include strategies which can tolerate the fault, which can handle the failure. So assume failure, measure everything, observability, automate recovery. If something goes wrong, recover, and we should automate it, automate recovery, limit toil, set timeouts, conduct blameless postmortems. This is very important. So let us suppose if system fails, something very bad happens to the system, instead of blaming one another, you should conduct post-mortem. Post-mortem is you should have a written document which should clearly describe the incident, the causes of it, the root cause of it, and what mitigation steps were taken, and the learning, like how we can learn from that failure and we can improve. So we should conduct blameless post-mortems and we should learn from incidents. So this is the reliability culture we are talking about, because here we are not at all, we are not just dependent on technological solutions for reliability, rather we are also considering the human element into the picture, the organization into the picture, because when we will be building systems, organization will be building system, so they have to have a mindset that they should welcome the failure, they should measure everything, automate recovery, limit toil, conduct blameless postmortems, and learn from incidents. So blameless culture is very important, because if we blame employees, if engineers, they fear punishment, like if you set penalties and all, if you cut down the salary for making mistakes, then what will happen? They will start hiding mistakes because of the fear. They will avoid reporting issues, and consequently reliability will degrade. So the organizational culture should not be like blaming one another, rather it should be blameless culture which should encourage learning. So the culture should be that, okay, something went wrong, it's totally fine, it's not your fault, it's the fault of the system, let's learn from that. Something was wrong with the system, that's why it went down, so we should learn from the incidents. So the culture should be to encourage learning, and with this system will improve over time. And we should also set error budgets. And what are error budgets? Error budgets are like we should define acceptable failure rate. So when we define acceptable failure rate, what will happen is that it will balance innovation with stability. It prevents over optimization of uptime. So this is the culture of reliability. So these are like some special techniques for building reliable systems, because reliability is not just about technology, it's also about organization, the reliability culture. Okay, synthesis. Reliability is layered. Okay, so see, reliable systems. So reliability is layered, meaning to say that reliability systems, if we talk about, they require observability, wherein we will be detecting the root cause of failure. Reliable systems, they require isolation, wherein we can contain the faults and failures, preventing it from spreading across the system. Reliable systems, they require redundancy, so that our system can survive, it can tolerate the failure, it can survive the faults and failures. Reliable systems, it require graceful degradation, so that system will keep on running with reduced features. And reliable systems, they require culture, and with this culture it will sustain improvement, because if the culture is blameless, every incident will be a learning which will improve the system, so sustain improvement. So reliability is an architectural property and an organizational discipline. So reliability we can achieve via architecture, like observability, isolation, redundancy, graceful degradation, they are architectural property. And also reliability is organizational discipline, the culture, the blameless culture. That's the organizational discipline, wherein any incident, do the post-mortem of it and learn from it and improve the system. That's the organizational discipline. So finally, we completed this lecture. So in this lecture, like we saw, monitoring detects known failures. Like monitoring is about like predefined metrics. We measure it in the real time. and it will alert the thresholds. Observability diagnoses the unknown failures, the root causes. So monitoring, it detects the known failures, and observability diagnoses the unknown failures. Graceful degradation, it preserves core functionality. Fail fast protects correctness. Redundancy observes hardware faults. Isolation prevents cascading failures. Reliability is also cultural. So the core designing data intensive application insight which we can take from this lecture. See, reliability is not about preventing failure. It is about surviving it intelligently. So I hope you got very good understanding of the concepts that we covered in this lecture. So do subscribe to our YouTube channel ScaleUp University for more such interesting courses and lectures. Thanks for watching. Thanks for your time.